over 1,000 pounds of thrust. That's what this engine produces at full power. It moves tons of air every single second and operates at temperatures exceeding 1,500 degrees Celsius. It's arguably one of the most impressive machines the human mind has ever engineered. But there's a problem nobody talks about. Every time this engine runs, it ingests dust, dirt, and sand. And that raises a genuinely unsettling question. If a handful of sand can destroy industrial machinery, what exactly happens when those same particles get sucked into a jet engine worth tens of millions of dollars? To answer that, you first need to understand how these machines actually work. How a jet engine really works. Most modern commercial aircraft use turbofan engines. At the front sits an enormous fan, sometimes over 3 meters in diameter. During takeoff, that fan pushes roughly 1.3 tons of air per second toward the rear of the engine. But here's something most people don't know. Only about 10% of that air actually enters the engine core. The other 90% flows around the outside and exits directly from the back. That small 10% is what drives the entire process. It first passes through multiple stages of compressors that raise its pressure to approximately 50 times atmospheric pressure. And compression does something interesting. It also raises temperature dramatically. Before the air even reaches the combustion chamber, it can already be close to 600 degrees Celsius. Then it enters combustion. Aviation fuel mixes with that superheated compressed air and ignites. The reaction releases enormous amounts of energy, and temperatures spike above 1,500 degrees Celsius. Now you have a stream of extremely hot, high-pressure gas that desperately wants to expand. But before it can escape, it must pass through several rows of turbine blades. Each turbine stage extracts energy from that gas flow. That energy drives the compressors and spins the massive fan up front. It's a counterintuitive idea. The rear of the engine is what actually powers everything at the front. In some modern engines, each individual high-pressure turbine blade can generate power comparable to a Formula One car. And there are dozens of them working simultaneously. When the gases finally exit through the rear, they generate thrust. But here's another surprise most people don't expect. In a modern commercial jet, exhaust gases produce less than 20% of total thrust. More than 80% comes simply from that front fan. That's why modern engines are so physically large. Why not burn all the air? If compressing more air and burning more fuel generates more power, why not send all the air through combustion? Some military fighters do exactly that. The problem is efficiency. From a pure physics standpoint, it's far more efficient to accelerate a large mass of air slightly than to accelerate a small mass of air to extreme velocities. That's why commercial engines have evolved toward increasingly larger fans. Burning less fuel is an obsession for every airline, and there's a fundamental reason behind it. Every thermal engine depends on a temperature difference. At 35,000 feet, outside air can be around minus 55 degrees Celsius. Inside the combustion chamber, temperatures exceed 1,500 degrees. The greater that difference, the higher the potential efficiency of the engine. But that creates a massive problem. The problem: how do you stop an engine from melting? Because technically, it should. The turbine blades sit directly behind the combustion zone. They're exposed to the full force of that superheated gas flow, while simultaneously spinning at extraordinary speeds. The tips of some blades approach 1,000 kilometers per hour, and because of that rotation, the forces trying to rip them from their mountings are enormous. A typical turbine blade weighs just a few hundred grams, but at full operating speed, it experiences forces equivalent to roughly 20 tons pulling on it constantly. That's like 2 double-decker buses hanging from a single metal component. While it's glowing red hot, and it gets worse. Hot oxygen attacks the metal through oxidation. Vibrations generate fatigue, and the air flowing through carries particles capable of eroding every surface they touch. For decades, engineers searched for materials capable of surviving that kind of punishment. Early engines used steel. It worked, but had serious limitations. As temperatures rose, steel lost its structural strength and began to deform. Then came titanium alloys. Titanium is significantly lighter, which helps reduce those enormous centrifugal forces on the blades. But titanium also reaches its limits when temperatures climb high enough. Engineers needed something better. The solution: nickel superalloys. The answer came in the form of nickel superalloys, one of the greatest achievements in the history of materials science. These aren't simply nickel. They contain chromium, cobalt, titanium, tantalum, molybdenum, and rhenium. Each element serves a precise function. Chromium improves oxidation resistance. Cobalt maintains structural stability. Molybdenum strengthens the metallic matrix. And rhenium, one of the rarest elements on Earth, dramatically improves resistance to deformation at extreme temperatures. But the chemical composition is only part of the story. What happens at the microscopic level is where things get genuinely fascinating. Inside these superalloys exist two structures known as the gamma phase and the gamma prime phase. The gamma phase allows a degree of ductility. The gamma prime phase acts as a barrier that blocks the movement of crystalline defects called dislocations. And that matters enormously, because dislocations are one of the primary causes of deformation in metals. The harder they are to move, the stronger the material becomes. That's why these alloys maintain their structural integrity even beyond 1000 degrees Celsius. But there was still another problem to solve. Single crystal blades. Even the best metallic alloys are made up of millions of tiny crystals called grains. The boundaries between those grains are relatively weak zones. At extreme temperatures, atoms can migrate more easily through those regions, which promotes deformation over time. Engineers found a remarkable solution. Eliminate the grain boundaries entirely. Instead of manufacturing blades from thousands of interlocking crystals, they began producing them from a single continuous crystal. That's how single crystal turbine blades were born. The manufacturing process requires extreme precision. The molten alloy is cooled very slowly as it passes through a spiral-shaped structure. That spiral progressively eliminates every forming crystal, except one. By the end of the process, the entire blade consists of a single crystal. More than 6 quintillion atoms perfectly aligned from base to tip. The difference in performance is enormous. Single crystal blades last several times longer than conventional designs. They withstand significantly higher temperatures. And thanks to them, modern engines can remain in service for tens of thousands of operating hours. But the temperatures are still too high. Even with single crystal superalloys, there's a deeply unsettling detail. The internal temperatures of the engine still exceed what the alloy can physically withstand on its own. So how do they prevent the blades from melting? The answer is hidden inside the blade itself. Modern turbine blades are hollow. During manufacturing, complex internal channels are created throughout the structure. A portion of the compressed air from the engine is diverted into those channels, cooling the blade from the inside out. But that's not all. That same air also exits through hundreds of microscopic holes distributed across the blade's surface. As it does, it forms a thin protective film between the metal and the stream of superheated gas flowing past it. This is called film cooling, and it's one of the primary reasons modern engines can operate at temperatures that should, by every logical measure, be impossible. Then comes another layer of defense: thermal barrier coatings. First, a metallic layer resistant to oxidation. On top of that, an ultra-resistant ceramic layer. Despite being only fractions of a millimeter thick, this coating can reduce metal temperature by 100 to 170 degrees Celsius. And this is precisely where the enemy enters. The enemy: sand. Many people assume that at high altitude, the air is perfectly clean. It isn't. The atmosphere contains mineral dust, microscopic particles, and, in certain regions, sand transported by high-altitude air currents. Volcanic ash represents a similar and equally serious threat. Every time an engine ingests air, it also absorbs small quantities of these particles. At first, that seems insignificant, but when you're talking about engines that process tons of air per second across thousands of operating hours, the consequences begin to accumulate. When sand reaches the hot section of the engine, something dangerous happens. The particles melt, and once molten, they begin to adhere to internal surfaces. Gradually, they can coat the ceramic thermal barrier coatings. They can penetrate the cooling systems. And this is where things become genuinely serious. The microscopic holes responsible for creating that protective cooling film can become blocked. If cooling airflow decreases, metal temperature rises. When metal temperature rises, material degradation accelerates. The thermal coating begins to break down. The superalloy becomes more exposed, and the operational lifespan of the turbine starts shrinking. How engineers fight back. This is why manufacturers like Rolls-Royce conduct extraordinarily rigorous testing programs. Real engines are mounted on test stands. Engineers then introduce controlled quantities of dust and particles that simulate sand or volcanic ash. What's remarkable is how little they actually need, often just a few spoonfuls per test cycle to study cumulative effects over time. Engineers analyze how coatings behave under particle exposure. They evaluate cooling system blockage patterns. They measure material degradation rates. And they use all of that data to develop the next generation of protective coatings and cooling architectures. Pay attention to this number. Some of the most recent coatings can extend turbine operational life by up to 30%. All to defeat an enemy as simple and as ancient as sand. And that's precisely what makes modern jet engines so endlessly fascinating. They don't just have to survive temperatures beyond their own melting point. They don't just have to withstand forces equivalent to dozens of tons pulling on them continuously. They also have to face millions of microscopic particles every flight. Particles trying to erode their surfaces, block their cooling systems, and accelerate their destruction, all while carrying millions of people safely around the planet every single day. The most impressive machine ever built by human hands. And its greatest enemy is a handful of sand. If you want more engineering stories that sound impossible but are completely real, there's another video on screen right now. Go watch it. I'll see you in the comments.